So we want to test for convergence, divergence in the following series, which goes from 0 to infinity. This is just to have a variable set up. Now, from 0 to infinity, the nth term a sub n is going to be set equal to, let's make it be n squared plus 1, n cubed plus 1. So the fact that the signs are the same, plus 1, is kind of a red flag there, because we would typically, if we want to use the ordinary comparison test, have plus minus or minus plus. But only one of those is going to work in the actual estimates we have to make. So if I was faced with this, the very first thing or question we might ask is, what do you folks think about it? Does it look like it's converging or divergent?
Diverging.
I would agree, because if it looked like this, I mean, we can't actually delete terms in the series, then that would be 1 over n, which is a divergent harmonic series. So I would start off by saying, let's let a sub n be n squared plus 1 divided by n cubed plus 1. Because we're trying to show that this diverges, again, that means that inequalities down here must go in that particular direction. What direction do you say they should go, less than or greater than?
Less than.
Turns out that would be for if this converges. If this is a convergent series, we'd want, or if this converges, we want to compare it to something, this, and we want to say that this would be larger than that diverging series. So we're trying to go larger if we suspect divergence. If we expect convergence here, and there would be convergence if we had power 4 like that, then we'd try to go less than. So here we can say we're going greater than because we suspect divergence. And well, it's true that if I look at the numerator, n squared plus 1 is greater than n squared divided by n cubed plus 1. So the estimates are going the right way. And let me pull up the notes for this so I can point to portions of the formula. Oh, but before I do any of that, welcome back, folks. Class has officially started. We're starting class with a question from before we started of how can we determine whether to use the comparison test or the limit comparison test. So in this problem, we're starting off by testing for convergence, divergence. We suspected that this is probably going to diverge because we want to compare it to this, n squared divided by n cubed, which is a divergent harmonic series. And when we use the comparison test, the key feature of that comparison test is if we suspect divergence, we have to be estimating with a greater than or equals to all the way through. So now once we go to the next step, where we have n cubed plus 1, which we'll replace with n cubed, it's true that if this is all there was, n cubed plus 1 is bigger than n cubed. That means in the reciprocal, 1 over n cubed plus 1, we would have a less than 1 over n cubed. And throwing n squared in the numerators doesn't change anything. So in other words, we now have a less than going this way. And this is a huge problem. So from this already, it tells us that the comparison test failed. And that's actually completely OK. If this was my exam problem and I found a failure of the comparison test, the last thing you want to do is erase the whole paper, because this is still work along the correct lines. So just keep on carrying on. Don't delete anything. Say that this is 1 over n, and give it a name, b sub n. It's in this specific situation where the inequality went the wrong way, or possibly we were never able to get this direction to begin with, that we're going to use the limit comparison test in set dead. So let's complete it with the b sub n. Since this is our review day, any questions so far with what we have? OK, so if you see a series, you suspect the comparison test would work, but there's a failure like this where the inequality goes the wrong way, then just keep on doing the normal steps, name the b sub n sequence, and we have to test a new series. So next, test the summation as n goes from 1 to infinity, b sub n. And by saying test it, that's just shorthand for test it for convergence or divergence. So it says we're going to test this, But occasionally, we don't necessarily have to test that at all. We could use, for example, the p-series test with p is equal to 1, divergent, or you could just say on the very get-go that this is a divergent harmonic series. So if you know the name of the series and the situation that occurs for that particular series, that's all you would have to say. And we'd consider that the complete test, just an identification, really. Any questions to that step so far? Okay, so the comparison test fails, but next in the limit comparison test, we take a look at the limit as n goes to infinity of a sub n divided by b sub n. Actually, you could put this in any order, but this is just a typical way to do it. This will turn into the limit as n goes to infinity of, first a sub n is n squared plus 1, divided by n cubed plus 1. It's multiplied by the reciprocal of b sub n, which is n divided by 1. So now we're dealing with the limit as n runs off to infinity of n cubed plus n divided by n cubed plus 1. But when n becomes very, very large, it's tending towards infinity, this gets closer and closer to n cubed divided by n cubed. So in the limit, we get a value of 1. Any questions with that so far? Okay, for me, this is where our complete list of tests for convergence and divergence starts to mess with my head a little bit, because I know if I see a 1, and I've been using ratio tests repeatedly, since that's just the section we've been in, I would say the test fails. But it didn't fail, because if we're going to the limit comparison test, we're trying to find if the limit turns out to come out at some value c, which is bigger than 0. It cannot be infinity. It has to exist. The conclusion is then, double right arrows means implies, both series have to diverge, because the one we compared it to diverge as well. And this is by the limit comparison test. We never said that anyway. Oh, we did. So if you said you're using the limit comparison test at some stage, some way, somehow, then you could just end it right at the conclusion that both diverge. Any questions with that so far? Okay, so if the comparison test fails, immediately just run to the limit comparison test. Other questions so far that folks would like to start out with? Okay, maybe just a couple reminders for the exam that's going to be next class. On that upcoming exam, we're going to go with this document here for the handout for the notes, which means it's not going to be printed in color, and there won't be any back to it. But things that you might want to add to your note card are things along the lines of, let me put these documents next to each other. You probably would want to have this right here, the alternating series test. Or not, excuse me, the absolute convergence test would be something you ought to have on there, since that's not on the flow chart. The next thing that I would probably throw on there is the alternating series estimation theorem. This one is also not on the flow chart, and it's a great question, I would say, because it allows us to say, how would you even estimate this if you had to, and how you would determine what the magnitude of the error in that estimation would actually be. It'd be fun to do this one, but we didn't actually do that as part of our homework, so we're skipping the integral test estimation theorem. So get the alternating series estimation theorem and the absolute convergence test, and you will have, I think, all the necessary parts. Then for your note card, you're allowed to put anything else you'd like on it. I'd probably put things like antiderivatives. Because there is an integral test on it, it means you have to have a good plethora of antiderivatives of things like, say, 1 over 1 plus x squared dx. That is tangent inverse x plus a constant. That's an important fact, which could be a high-stakes kind of formula if it's required for further steps in a larger problem. So I would go with those two formulas and antiderivatives. Beyond that, it's really up to you folks. Other questions about the upcoming exam 3? Okay, so the upcoming exam 3 goes all the way to chapter or section 11.10. We didn't cover everything in 11.10, so a really great guide on what would actually be an 11.10 question would just be the problems that we had done on the board last couple classes from that section. Other things that we should be aware of for the exam is that it is closed calculator, but it is open note card, so you folks are welcome to come grab a few of these if you'd like at the end of class. I think that's all the announcements I have so far. At this point, we'll return that time to folks for questions that you'd like to ask, and we can go from there. So what other questions do folks have about sequences and series? It's a really broad question, right?
Could we do a few problems from 1110?
Yeah, I'd be happy to. So from 1110 specifically, there's a couple problems that I would likely ask. Keep in mind that when you go over the sample exams that are available here, I can't ask every single question, so I just have to pick some of my favorite ones. And from 1110, it could be one or both of these two questions. First, let's do the standard question, which says, find the Taylor series representation of our function is going to be f of x equals 1 divided by x centered at a, which is always the variable we'd like to use for the center in formulas. Let's let the center be 2. Since we've been letting it be 1 too many times. So we'll do the Taylor series representation of this function f of x. This was a real guy, so let's put him in uppercase. And let's put an extra set of instructions that says, using the definition of Taylor series. This means there may be a Taylor series provided for 1 over x, or we're going to build it up purely through scratch. Any questions then about the statement of the problem? Probably I'd add a little bit extra to this if it was an actual exam problem. I'd probably say, then stop, do not find the radius nor interval of convergence. So some of the problems on the actual exam have further instructions to tell you to move on to the next problem. So whenever you see something that says, then stop on the exam question, that's really just for the time's sake. There may be more that you could say about that series, its radius or interval of convergence, but that would be like doing 3 or 4 problems if we did everything. So we're just going to find the representation and move on to control the length of these problems. So keep a keen eye for this kind of stuff. First, we start off by a 2-column system using f of x. It's defined to be 1 over x, but we're going to be taking derivatives. So for me, it's easier to write it as x to the power of -1. Then in the second column, we evaluate f at that center. So we immediately write f at 2 would be 2 to the power of -1. And we're off to a start. So using the definition of Taylor series means our goal is to come up with this, a formula for the nth derivative of f at the center, which is 2. If we can come up with that formula, then the problem is essentially over. We still have some writing to do just to summarize. So let's go off as many rows as we need just to settle the pattern. Some of these could require a good many rows, especially if you have things alternating with zeros. We think we've done like 6 or 9 rows before. But for the purposes of the exam, if you have 3 rows and you can see what the pattern should be, that would be sufficient work. So go for at least 3. I would say 4 or 5 is probably a little bit better to really see that pattern. But now here, this is f prime at x, which by the power rule becomes negative, x to the power of -2, and we'll go from there. Immediately then, calculate f prime at 2, which would be -2 to the power of -2. So already it does seem like we have a pattern. We started with something positive, 2 inverse, then we went to negative 2 power -2. It also looks like the powers here are climbing by 1. So if we feel like that's still the case, if this becomes a positive 2 to the power -3, then I might be convinced we have a pattern down. But let's see what happens. Next is f double prime at x, which becomes -1 times -2, x to the power of -3, and that is a pattern breaker all of a sudden. But That's okay, it just means I might go for a fourth or fifth row in this problem. This has broken the pattern due to the 2, because now if we go to f double prime at 2, we'll get positive 2 times 2 to the power of negative 3. And one thing, again, this sounds really weird, because it goes completely against our training in algebra. You don't want to simplify that, because if I simplify 2 times 2 to the power negative 3, I'm going to damage my chances of coming up with this formula down here. So leaving things in factor form like this aids in the pattern seeking. Any questions so far? Anyone happen to see the pattern for the nth derivative at 2 at this stage? Okay, if you don't see it, that's okay. Just go on to the next line. And if we got stuck here, you could just say, tell me how the problem should proceed. If you tell me that you know that our goal is to find the nth derivative at the center, and then summarize by saying the power series is summation as n goes from 0 to infinity of fn at 2 divided by n factorial times x minus 2 to the power of n is equal to 1 over x, then I would give a substantial amount of partial credit for that. Because you are saying you're giving knowledge of how the problem should proceed, and that's the whole point of the exam itself, is to determine your understanding of these kinds of problems. So if you get stuck at any stage, then just give me some description on what should happen next, using ordinary sentences. That's weird to do in a math class. Let's go off to the third derivative. F triple prime, we start to write this way if you like. This would be negative 3. Remember, we don't want to multiply things together, except negative signs, because that would get out of control if we didn't multiply those. So I have negative 3 times 2, x to the power of negative 3, which means f at the third derivative at 2 would be negative 3 times this 2 times 2 to the power of negative 3. Or sorry, say again? Oh, yes, sorry, forgot how to do different derivatives right there. So the new power of negative 4.
And the other one.
Oh, right. That's the trouble with errors is they cascade. So good thing that was first error on that line, not at the very first step. Does that look better so far, folks? Okay. So it looks like there is possibly something going on so far. And let's see what's happening with this stuff at the moment.
It's factorial.
Yeah, we have a factorial situation. So we can start to write this as, it looks like this one was negative 3 factorial times 2 to the power negative 4. Then this one simplifies as positive, and we have 2 is equal to 2 factorial. So this 2 factorial is 2 times 1, times 2 to the power of negative 3. This one becomes negative 1 factorial. Since there's really a negative 1 here if we'd like, and 1 factorial is 1, times 2 to the power negative 2. And the original one, we can always insert a 1 there, and this looks weird, but 1 factorial is 1 by definition, and by convention, 0 factorial is also 1. So if we insert a 1 times 2 inverse, that's in fact a 0 factorial times 2 inverse. That means this pattern that's emerging should now support us on getting the nth derivative of f at 2. Any questions before we try it out? Okay, so when we're writing down this pattern, one key issue is we have to be careful of the indexing. With the indexing we think of this as 0 because this is not technically correct, but I think of it as the 0th derivative. Then finally, this is the first derivative. And that's the only reason we're starting at 0 when we look at power series, because we're thinking of derivatives. So it goes 0, 1, 2 for indexing. We got up to 3. And if that's the case, we can start off by handling the alternating feature that we see. Starts off as positive, negative, and that pattern should continue to get negative 1 to the power of n. How do you folks feel about this? Is it going to be n or n plus 1 in this situation?
N plus 1.
So if we go with n plus 1, typically that would work, except for we're starting at 0. So that's kind of nasty. That's a good thing to always write down here when we produce this list. If we start at 0, plug in 0 there would give us negative 1 to power 1, which would start us at negative. So in this situation, we need to start at just a power n on it. So when we put in the index 0, negative 1 to power 0 gives us the positive 1 to start with. Does that make sense so far? Okay, then for index 0, we have 0th derivative. 1, we have first, not derivative, factorial. 1, we have 1 factorial, so on down the line. So we can say if it's the nth derivative, there should be an n factorial in the problem. So that would be the next component. Then we have to throw in the next portion of the pattern we see. We have 2 to a negative power, so this would be 2, but to what actual power? Anyone happen to see it?
Negative n minus 1?
It'd be negative n plus 1 or negative n minus 1, just depending on how you mean it. So I wrote it this way because I'm thinking of 3 went down to negative 4. So if I have n, it should be n plus 1 and negative to match up this pattern from here to here. Does that make sense with that so far? Okay, at this stage, the problem is really kind of nearly done. All we have to do is summarize by putting the expression for fn at 2 into the power series. So to summarize, the Taylor series representation of 1 over x, chalk feels funny. Feels like the cheap stuff, sorry. The Taylor series representation of 1 over x at the center of 2 is now summation as n goes from 0 to infinity of, we still have an n factorial, which we started from, x minus 2 to the power of n, we already threw in as part of our summary, and it's this stuff that we produced. So all we have to do is copy in negative 1 to the n factorial to the power of negative n plus 1. This is one of those problems that just does not want to quit. Since algebraically, if you have something like this, we do have to always reduce all fractions. So the very last step, this would be a very low-stake step. Maybe you could lose a quarter of a single point. But the very last step is you do have to reduce. So do a cancellation there, and the simplified power series representation is a summation from 0 to infinity of negative 1 to the power of n. We could go x minus 2 to the power of n. And if you prefer, you can make this to be 2 to the power of positive n plus 1. But that's not really the critical thing at that step, really just the cancellation. So if you see obvious and immediate cancellations, you should go for it as your last step. If it is something that requires multiple steps to reduce, it'd be okay to just leave it at that stage. Any questions with that kind of problem so far? Okay, so there'll be a problem that looks like this on the exam. And when you get your exam, there is an unintended set of hints on there. Some of the problems, you have an entire page to work out. And some of the problems, you have something like 10% of the page for space. So if you have an entire page, it means you're just expected to write out lots of details like on this problem. And if there's only a little bit of space, probably there's actually hardly any work to do at all. So also keep that in mind when you solve the exam. But let's go off to the second kind of problem that you could get from this chapter of 11.10. But before that, any questions that folks would like to discuss about this one? Okay, so this is how a second problem could work. It's going to start off by saying the Taylor, or rather the Maclaurin, just sounded how still, the Maclaurin series representation of cosine of x is cosine of x equals the summation as n goes from 0 to infinity of negative 1 to the power of n, x to the power of 2n, since cosine is an even function. That's a good way to memorize this set of formulas by putting in 2n, which is always even, s divided by 2n factorial. So there's a lot of instructions on this problem. This is one of those problems that's a full sheet, possibly. So we have a Maclaurin series representation. And by the way, before we get too far, what makes this one a Maclaurin series and not a Taylor series? Anyone happen to know on this problem?
It doesn't have that x minus 2.
Exactly. We really have, say, an x minus 0. So it's a Maclaurin series because the center is equals 0. So whenever you see Maclaurin series referred to, it's just a special case of the Taylor series. That's an important fact to keep in mind. Okay, so the problem is still being built. The instructions are we have a Maclaurin series representation. You don't have to prove this. You can just take it for granted. It's also going to tell us the radius of convergence is something, and this problem, it's infinity. Instructions then go on to say, to find the antiderivative below as a power series. Then state its radius of convergence. That is a lot of instructions for one problem, but really the instructions in some sense are more important than the problem if you're thinking about exams, because if you see those sort of instructions again, I might change the wording just a little bit, hard to get it copied verbatim, but if you see these instructions, you'll know about what you're doing and what we're going for the steps. So the first thing we need to do to find the antiderivative, the problem is not done, sorry. This is the antiderivative we want. Cosine x to the power, divided by x to the power of -7 dx. So we need to solve that as an antiderivative. That's an interesting problem because we, in fact, can solve this using, anyone happen to know what the technique might be? In a long time. It could be solved using integration by parts 7 times. So that is a heck of a thing to do. Or there are shorthands, but your column is going to involve a whole bunch of derivatives, and it's a lot of work to write all that out. So we're going to do it in a slightly nicer way. The downside is the answer is going to be a power series. But this is still a nice technique in the sense that if this was x to the power +7 in the denominator, then that is more likely than not an impossible antiderivative, much like the antiderivative of e to the x squared. So even though this one is possible, it is very, very impractical, and it could have well been x to the power of -71, and the steps are still the same, and now it cannot be done in the amount of paper provided. But this is what I would do for the solution. We are taking cosine x, divided by x to the power of -7 dx. And first we make a substitution. Cosine x itself is always equal to this for any value of x that you pick, since the interval of convergence is now all real numbers due to that radius. So now this becomes the antiderivative of x to the power of 7. I'll bump it to the numerator, make this a +7, times the summation from 0 to infinity of cosine, which is -1 to the n, x to the 2n divided by 2n factorial, and then a dx on the very end. So we need to solve that problem. It looks really, really terrible. But actually this problem, where we ended on this as an answer, this is the longer, tougher problem, I would say. All we really have to do in this problem to solve the entire thing is rewrite this as summation from 0 to infinity. At the same time, let's move our integral sign inside and make this be x to the power of 2n plus 7 divided by 2n factorial dx. So I've done a couple things. I've taken the x7, combined it with the x to the power of 2n, and that's why I have a power 2n plus 7 on the inside. The second step is from a very, very technical theorem in section 11.9, integrating infinitely many terms when the radius is larger than 0, and we qualify infinity to be larger than 0 in this context, is just a matter of interchanging where the integral sign is. It can commute past the infinite sum and become the antiderivative of the nth term. And the only thing that could possibly change when we take the antiderivative with respect to x is this portion. The -1 to the n and the 2n factorial are effectively constants with respect to integration so far. They're not constant with respect to summation, but any questions to that step? Okay, so next we just need to use the good old power rule, which says if you have x to the power of n and you want the antiderivative, this is always equal to x to the power of 1 higher, n plus 1, divide by n plus 1. Need an arbitrary constant. Hopefully I didn't kill that. So we'll do that same thing with x to the power of 2n plus 7. The new power will be 2n plus 8. So this is the summation as we go from 0 to infinity of negative 1 power n, x to the power of 2n plus 8. Down below, we have to divide by the new power, 2n plus 8, much like we did in the formula. Then we multiply it by 2n factorial. And I think we nearly have it. Any questions to that step so far? OK, so we're missing two things, really. One thing we're missing is the radius that we need to state. But we're also missing one thing in our antiderivative. Anyone happen to see it? Right, we need the constant of integration, so we have to throw on a plus c. I'll move it way over here to just try to communicate that the summation is with respect to all of this stuff inside here. If we had, for example, summation going this way, and c is not 0, then that would have been divergence, because we're adding infinitely many terms that are non-zero. So I'd throw it way out here, or maybe just out in front, to communicate that plus c is not part of the summation. It's added on after the fact. Then the last thing to do is, the problem says, then state the radius of convergence. And typically on these exams, when you're told to just state something, it means you don't have to show the work. So I don't have to take this, hit it with the ratio test or anything along those lines. I mean, we could do that, but it is a lot of extra work. And we do have a really, really huge theorem that's working in the background to help us. But before we look at that theorem, anyone see what the radius of convergence should be so far? The trick to this is it's simply r equals, I shouldn't say simply, but it's also r is equal to infinity. So that's a really important fact. You could check it out as well if you use the ratio test. But because the problem said to just state the radius of convergence, there's no work necessary. You just have to say what it is. And that r equals infinity came from this down below. So that is possibly something you may want to put on your note card. But if you put this theorem on your note card, you might want to compactify it because it's really, really big. It says a lot of things. It's trying to communicate what's happening when you take the derivative of a power series. So that's this line. At the same time, there's a formula for when you take the antiderivative of a power series. It says we can do just what we did. We interchange the summation of infinitely many terms with the integration sign. And whenever you do that, it'll have the same radius and the same interval of convergence, whether we use the differentiation formula or the integration formula. So that means we can just state, once we know a radius here, it cannot possibly change through differentiation, no matter how many times, or anti-differentiation, no matter how many times we do it. So that's a really, really helpful tool that, once again, a lot of these theorems are just trying to control the length of the exam. So if you're aware of these theorems, you wouldn't have to do the ratio test, and you could save a lot of time on this one. But any questions with that so far? OK. And also, if you're not sure on an exam, you can always ask if enough work has been provided. It's kind of a touchy question because if the answer of is enough work provided part of the exam question, then I can't answer it. But you're always welcome to ask. Let's go off then to another question. So this concludes the two types of problems that you could possibly see from Chapter 10. These are the major things we've done. There's more information in Chapter 10 that we're going to cover, but that's as far as we've went. Other questions that folks would like to discuss next? OK, how about for the sake of review, just we have already something on the chalkboard. We could say for a part B to this problem, it would really be a whole new problem. But let's actually find the radius of convergence to this thing. That's just a decent problem in its own right. So let's say, as an entirely separate problem, it starts off by saying, find the radius and interval of convergence of the power series which is summation from 0 to infinity negative 1 to the power of n, x to the power of 2n plus 8 divided by 2n plus 8 times 2n factorial. So we want the radius and interval convergence of that thing. Any questions about that so far? Okay, we're calling this thing a power series only because of the x variable. And we're asking for the interval of convergence and the radius of convergence, once again, only because that's going to depend on the variable x itself. And when we have a power series, there's two tests on the table. We can use the root test, or we could use the ratio test. I would only use a root test if everything had a power of n on it. So because this is not 2n factorial to the power of n, the root test would be a bad idea. Instead, we can use the ratio test. And the ratio test shows convergence. This is absolute convergence when, this is a really long sentence, we're going to do the limit and say less than 1 on the limit. And that's when we have convergence through the ratio test. So let's do the limit next. It'll be limit as n goes to infinity of an plus 1 divided by a sub n. I mean, you never really have to copy this step, but I think it's a good idea because it just sets the mind of how the process should proceed. If we write this as an plus 1, it means we're thinking of this as the an, and we're putting plus 1 everywhere. So this is going to be the limit as n goes to infinity of absolute value will be negative 1 to the power of n plus 1. But if we put n plus 1 inside here for the power on x, it would be 2 n plus 1 plus 8. So this power works out to a 2n plus 2 plus 8. So it's x to the power of 2n plus 10, which is unexpected. For me, it's a common mistake, kind of an embarrassing mistake, to say it's 2n plus 9, but really 2n plus 10. Does that make sense why? Okay, really just because of the distribution here to here with the 2, n plus 1 causes us to get a 2n plus 10 altogether. Then down below, we're putting a 2 there, or excuse me, an n plus 1 there, so it's the same kind of deal. We'll have a 2n plus 10, or putting a 2 here, so that 2n factorial, or excuse me, 2 n plus 1 factorial becomes 2n plus 2 factorial altogether. Does that make sense to that step so far? Okay, then because we're working with absolute values, or excuse me, with factorials in this situation, it's a very good idea to re-express this in a new way. So what would be a better way to write 2n plus 2 factorial in this context of ratio test? It would be we get a 2n plus 2 to start, and then when we do a factorial, what would be the very, very next term after that? Anyone see it? It'd be exactly, you have to descend by 1 every time. So just like 6 factorial means 6 times 5 times 4 times 3 times 2 times 1, what we've done so far is the thing playing the role of 6 is the 2n, that's going to look crazy, 2n plus 2. Then we go to 1 less, much like the 5. It'd be a 2n plus 1. But one thing that we could always do is we could also say that this is 6 times 5 times 4, 3, 2, 1 is a 4 factorial. So we can cut the factorial short and just write out the first couple terms if we like. The only reason we're doing this is because we're throwing extra stuff here, causing a cancellation. So because of an expected cancellation, we're going to say 2n plus 2 factorial is 2n plus 2, 2n plus 1, times 2n factorial, all multiplied together. Any questions with that so far? Okay, so we have a huge mess, but it is what it is. So from the factorial, we have a 2n plus 2, 2n plus 1, and a 2n factorial, which means that fraction needed to be a little bit bigger. And now we divide by a sub n. So the reciprocal of a sub n comes in as a 2n plus 8 times a 2n factorial divided by -1 to the power n times x to the power of 2n plus 8. So that's where we're at so far. Is that all right with folks if I erase this scratch right here? Okay. But once you get to this step, this is essentially the fun part, right? Where we get to cancel all these terms in a step-by-step way. Starting with absolute value is going to kill off the -1 to the power n, -1 to the power n plus 1 portion. So all of that stuff is definitely gone. Next interesting cancellation is the 2n plus 8 with 2n plus 10. Nothing can happen. But we do have a 2n factorial. Here to here we can cancel off. And we can always cancel off powers of x. Because with a 2n plus 8, canceling it into a 2n plus 10, 2n plus 10 divided by a 2n plus 8 would give us just an x squared altogether. Does that make sense with that cancellation? Okay, so if you cancel all of this here into all of this, and x squared is the sole survivor. Since all we're really doing in essence with that cancellation is a subtraction of powers. So now I think we're ready to write out this limit. It's equal to, I would take this x squared and always bring it outside the limit in this way. Typically we'll have absolute values on it. I'll write it in that step this time. But this time the absolute value would fall off on the next step because x squared is always positive. So we pulled out variable x because it's constant with respect to the limit as n goes to infinity. And we should always look for more constants, but I think that's it. So now we just write the limit. As n goes to infinity, copy down all the things that did not survive a cancellation, n depends upon a. So across the numerator, we've already pulled out x squared. We have a 2n plus 8 divided by, the denominator has a whole bunch of stuff, a 2n plus 10 times a 2n plus 2 times a 2n plus 1. So we need to take that as a limit. It looks like a horrendous limit, but remember we have specific protocols for this situation. If you need to work out this as a limit, think of this as a rational function, which you could plot in the xy plane. What would be the horizontal asymptote of that rational function? Not quite. Close. It'd be 0, correct. The reason for that is we don't actually want to do it. But if we did do this, we could say it's equal to the limit. I'm going to erase all this stuff. But just to highlight what we're looking at, if we multiply all three terms together, that is a process, but we would get 8n cubed and a whole bunch of other stuff as we did all the necessary distributions. That would be over 2n plus 8. But because of the power 1 here, I forgot my x squared. Because of the power 1 here and because of the power 3, that must be a limit 0. The whole thing is going to get closer and closer to 0 as n becomes large. But because it has that higher power in the denominator, the whole limit becomes x squared. X squared is unaffected by the limit, but it's multiplied by 0, and the ratio test shows convergence, absolute convergence, when this is less than 1. So we finished off a very long sentence. But 0 times x squared is always less than 1. So this is, let me write this in a different way. It's equal to 0, which is always less than 1. And so we're ready to state the radius and interval of convergence. So in this specific situation, where the limit comes out to 0, it's almost a trick question. Anyone see what the radius should be then? It is infinity, correct. Because we're getting this conclusion of the limit is 0, which is less than 1. That does not depend on x whatsoever. You can pick as crazy as an x you like. You could pick pi to the power of 10 million. Then square it times 0. We still have 0 less than 1 for convergence. That means we have convergence on a radius, which is infinite, and an interval, which goes from negative infinity to positive infinity, or that you could write as just double r like that, to say that it's the set of all real numbers. So that's the kind of problem that you could do for just the sake of looking at how to test a power series to find its interval and radius of convergence. But we did that also, not just as practice, but to tie back to the fact that once you have the radius is infinity and you integrate something that has a constant multiple of a power series, then this cannot possibly change. I mean, this was not a proof. It highlights how the actual theorem is working. And it's also a reminder, if something says to just state a radius, you really don't want to do all that work. That's a whole separate problem in and of itself. Any questions with these two problems so far? Okay, so we've discussed comparison tests, Taylor series, an application of Taylor series, this problem, as well as power series. What other questions would folks like to discuss so far? Well, part of this exam is there's going to be one problem worth 18 points out of 78 points. Sorry, 78 just made sense on this exam. But there'll be one problem with 3 parts worth 18 points where your sole job is to just pick the correct test. So maybe we could do something along those lines right now. Does that sound all right to folks? Okay, so I'm going to just throw random series on the chalkboard. It'll be our job to determine whether it converges or diverges, working out the steps as we've done before in class and in homework, and picking the own test that we'd like to pick. One hint to this problem is that if you're told to test for convergence divergence using any test, probably the one test you should not use is the integral test, because there's going to be one problem that specifically says use the integral test here. And again, the whole reason for that is to control the length of the exam. The integral test may work on a lot of problems, but if we use the integral test on every problem it works on, the exam is just going to be too long, and some of those antiderivatives may be not very approachable at all. So keep that in mind. I would probably not use the integral test unless I'm told to do so. That's a horrible way to say it, but that's just for the benefit of not taking too long to do the problems. So now for our power series, let's look at the summation as n goes from 2 to infinity for 2n minus 2 divided by n squared minus 2n plus 1. And this problem says to test for convergence, divergence. But there's a lot that goes into that. We have to use proper limit notations whenever limits come up. We have to state the test that we're going to use, show all of its hypotheses, and we have to clearly state what the conclusion would be. And I miscopied this. That's a power 2. Okay, so first, let's just take a moment to analyze this and decide what test could possibly work. So let me pull up the sequences and series flowchart, since this is going to be handed out to every person during the exam. It won't be in color, so pretend you're colorblind. Test for divergence would be the one on this one. The way you can tell a test for divergence would work is we want to just kind of imagine what would happen if we took this limit, 2n squared minus 2 divided by n squared minus 2n plus 1. So before we even select a test, I would probably just imagine this in your mental blackboard. What would be the value of that limit? It has to be a value 2. And the reason this time we get a value 2 instead of 0, like in the last problem, is because of the tie on the exponents. Whenever we have a tie on the exponents, the horizontal asymptote is formed by pulling off coefficients, which are 2 from the numerator and a coefficient 1 belonging to n squared from the denominator. So the limit is 2, which is not equal to 0. That means the original series will diverge by the test for divergence. And when you read this flowchart, keep in mind that the test for divergence, in some very, very real sense, is the most trickiest test in the entire chapter of 11, because there's only one conclusion. So when you go to take the limit in this flowchart, it asks you the question, is the limit 0? And I would say no, and now my conclusion is divergence. But notice there is only one direction in this flowchart, which is trying to communicate that by this theorem, you can only conclude divergence and nothing else. So I can never actually use the test for divergence and give a convergence conclusion on my series, which is horrible. And the harmonic series is a counterexample of why that can't work. With the harmonic series, the limit of the nth term is 0. However, the series does diverge, as you could check with the p-series or integral test. So this problem is done once you say diverges by test for divergence. So that problem with 3 parts, it's going to look long because you have to test 3 different series. Some of those tests, or some of those series might require multiple tests. But actually, once you get the knack for this, there's really not a lot of details to write. So we're off to the next part. Any questions at all, however, with this one? Okay, so let's go off to something that is maybe a bit more of a chore. Always keep in mind the test for divergence is still on the table for this exam because it comes up in all sorts of contexts. It could have came up in this problem if the radius wasn't infinity, for example. So in the next series, I guess the hardest thing is to pick one. Let's try maybe n goes from 1 to infinity of the summation sine of n divided by 5 to the power n. So that's going to be our new series. First, let's just take a moment, give it a try, decide what could possibly work on this list. And the trouble with the alternating series test is, let's take a closer look at sine in Excel, which is a weird thing to do. Well, maybe a slightly faster way to do this, because we're running out of time, is the graph for sine looks about like this. So this is from 0 to 2 pi. But what's going to happen is, if we look at sine n and we plug in 1, that's already a problem. 1 is 1 radian, so it's going to be about here. Plug in 2. At pi over 2, we're going to be, I think, somewhere out here, possibly. If we plug in 3, that's going to be somewhere right here, because sine at pi is 0. Sine at 3, which is just shy of pi, would not give us a 0. So from here to here already, we went negative twice. Now sine n is not alternating. That's really, really frustrating. So this is not an alternating series. However, if it looked like this, and from 1 to infinity, sorry, say again? Yeah, if we go say, well, sine could also work in this context. Well, if we did go cosine, if we went cosine n, we would have the same problem. What we need to do is go sine, do something like pi divided by 2, because sine pi divided by 2 is 1. And if we go sine divided by 3 pi over 2, that would be negative 1. So if we go plus pi n, then this is going to be something that goes like this. When n is 1, we're at 3 pi over 2, and sine takes on negative 1. When n is 2, we're going to be back to 5 pi over 2. When n is 2, and we be back to a positive 1. So because of the pi over 2, this one would alternate between negative and positive. Another one, if we did it with cosine, would look like this. Cosine of, let's let it be n pi, divided by 5 to the power n. So if we got that over here, these two would be alternating. Because if we plug in 1, cosine of n pi takes us here, which is negative 1. Plug in 2, cosine of 2 pi would take us here, which is a positive 1. So these two alternate. But this one is horrible because we took away the potential for it to alternate by just going sine n. So sine n, cosine n, tangent n all have that same problem. Well, that's okay. We can still work through it. But we do need another test. Let's see what could be the next test to choose. Comparison test would work, yeah. So either the comparison test or the limit comparison test would work on this one. So the trick to this one is, another important feature about the sine wave is it's bounded. We have a upper bound of 1 and a lower bound of negative 1. And this means that sine of n is always less than 1 or equal to it. But because n is discrete, we could just say less than 1 if we'd like. It's only ever equal to exactly 1 at a certain multiple of pi over 2. So we can say that it's really less than 1, and it's bigger than negative 1. But this already, as an estimate, allows us to use a comparison test to start this off. So we can say, by the comparison test, so my strategy of saying by the comparison test is, now I'm not going to forget to indicate the test I'm using, because we've already mentioned it. We can say by the comparison test, since a sub n, which is meant to be the nth term of this series, sine n divided by 5 to the power of n is less than 1, because sine n itself is less than 1 over 5 to the power of 5n, which will set equal to a b sub n. So by the comparison test, since we have this estimate and the summation, as n goes from 0, no, 1, starting to forget, we're starting at 1 with these, 1 to infinity of b sub n, well, now we have to test this thing for convergence or divergence. So this is kind of a scary thing with testing series from convergence divergence, because we worry if this could ever become an infinite regress of more and more tests. But keep in mind, if you use the comparison test, you have to use a separate test to test the series you're comparing it to. So the format of this series is a summation from 1 to infinity of 1 over 5 to the n. So now we ask ourselves, is that a p-series or a geometric series? Looking up there, since that's handed out on the actual exam. It's geometric, exactly. What makes this geometric is the n itself is only presented as an exponent. So this is a geoseries with common ratio r equals 1/5. And if we look at this flowchart, it says for the geometric series, I cannot read that. That is very, very bright. Let me try again. So go back to the geometric series, and it says, does a sub l equal a to the power of l minus 1? We're going to say yes. Here, this yes just means, yes, it's a geometric series. Further question asks, is the common ratio r less than 1? Yeah, that's the case in our situation. R is 1/5. A fifth is less than 1. So by our flow chart, we have a yes here. But that yes now tells us we're in convergence. Here they said it in a really weird way. They said the total series with respect to a sub n is equal to a divided by 1 minus r. But this is also telling us it converges. If you can say it's equal to something, that's always a statement of convergence. For us, this is all we need to write. It converges. Oh, I spelled it right. Converges. Okay, so let's start off back to this original, very long, possibly a run-on sentence. It says, by the comparison test, since we have an estimate, and it's being compared to a b sub n, which converges by the geometric series test, the original series converges. And that finishes off that one. So if you have to use a comparison test, we really did write out a lot of details, but keep in mind, really the major work was here, making the estimate, here picking the nth term, so the sequence, and going here to test this as a series. Then once you do that test, if we had convergence, and if the inequality goes the right way, we can say the original thing does converge. If the inequality didn't work out, if I had a greater than, for example, then I would just have used the limit comparison test instead. Any questions so far with that one? Okay, let's try maybe one more, and then we can switch gears if folks like. So the very next one reads, let's go from 1 to infinity of negative 1 to the power n minus 1 divided by the natural logarithm of n plus 1. So that's our new series. First, we just want to take a moment, meditate, consider it, and also consider our flow chart. So the format of this series, and what we see on our flow chart, what test could be used on this one? Yeah, in the alternating series test, the things that we want to look for is there should be an alternating portion to the problem. So we have to have something that looks like this, a negative 1 to the power of n. And probably the best thing to do whenever you use the alternating series test, we've decided, yes, we do meet that situation because we have negative 1 to the power of n minus 1. but we need to come up with the b sub n, because in this box contains all the conditions that we would like. This tells us that the b sub n as a sequence is decreasing. Note that there is no notion of decreasing as a series. And the limit of the sequence, again, not of the series, should be 0 itself. So let's check that out. But first thing we have to do is decide on what is the b sub n. And here we're using the alternating series test, where what would you folks say the b sub n should be in this problem? Exactly. We extract from the problem everything except the component that makes it alternate. So we get 1 over natural log n plus 1, as you said. Then we have to check some conditions. Some of the conditions on this exam are really just stating them. So if you look at this, would you folks believe that's decreasing as a sequence? Yeah, the reason this is decreasing is because the natural logarithm is an increasing function. So I have something growing larger and larger in the denominator, a numerator which is always constant. That means this gets smaller as n grows larger. So all you really have to say is, then b sub n, I'm writing it this way because it is decreasing as a sequence. And we have to do one more step. We need to take the limit. And the limit, as n goes to infinity, of 1 over the natural log of n plus 1, what should this be as a limit? Yeah, this comes out as exactly 0. Again, there's really no work to show for that. We know it should be 0 because we have constant divided by something that grows ever larger without bound, which always gives us a limit 0, and by the same token, tells us that the sequence is decreasing. So notice, I really am just stating these things. You do have to state them for the exam, but there's really not a whole lot to do. The last thing to do is we say the series, the original series, a sub n, converges. By a sub n, we mean this one. If you just want to refer to a series rapidly, you don't have to do the n equals 1 to infinity. Just the sigma symbol would be sufficient. So if it's an alternating series, that's almost like a freebie because there's not a lot to do. Same with the test for divergence. But the thing that's very, very tricky about this problem is the alternating series test can fail. And another thing to keep in mind is that there is only one conclusion, convergence. So if we suspect that the series alternates and that it diverges, we cannot actually use this test. That's kind of interesting. Let's make a comment for the next problem on what the test would actually be. So let's suppose it was from 1 to infinity, summation, and let's let it be negative 1 to the power of n, so it's alternating. Throw in a 2n minus 2, and let's put this to the power of 2 like before. I'm really just grabbing that one over there. In the denominator, it has n squared minus 2n plus 1. So if you had this as the series, now it's alternating, and we can say, since lim as n goes to infinity of 2n squared minus 2 divided by n squared minus 2n plus 1 equals 2, the alternating series test, would you folks say that's okay as an acronym? AST for alternating series test? Okay, if you start running out of time or space, then that's a decent acronym. So if you wrote something like LCT, I'd assume you meant limit comparison test and things like that. So by the alternating series test, it fails because the limit has to be 0 in that specific test. So the very next test is the test for our divergence. We can say, but the limit as n goes to infinity of negative 1 to the power of n, 2n squared minus 2 divided by n squared minus 2n plus 1, what can we say about this as a limit? It turns out it's not quite 0. It's not even 2, which is kind of weird. This is a does not exist. So what's happened is, if this limit right here comes out to a 2, and the only difference on the new limit is something that's alternating, it means the sequence is really diverging. One half of the sequence is climbing up to 2. The other half of the sequence is climbing down to -2. So the terms of this series are bouncing between values that get closer and closer to 2 and -2 at the same exact time, which means the limit cannot exist because the limit to exist has to approach one number, not 2. So this does not exist. But this means we have a conclusion of divergence by the test for divergence. Because that limit down below, it certainly does not equal 0. So we have a no on the flowchart. It's even worse, it doesn't even exist to begin with. Any questions with that one? Okay, we're down to 3.5 minutes. What other questions do folks have so far? Okay, maybe one last piece of advice. I think one of the problems, I'm not sure which problem, the exam is not meant to be scrambled, but it's not exactly in order either. But one of the problems is going to say to do the following. Test for divergence / convergence. It'll say in bold, using the, and it may say a couple things. So it might tell you to use a specific test. It may say the integral test, the ratio test, or the root test. So some of the problems like we've just been doing, we choose the test. But I do have at least one question that will say, use this specific test. So if you see the problem that says test for divergence convergence using the integral test, then we really have to use the integral test for full credit. If you're not sure, or if so you get stuck using the integral test, and you find another test that would work, I would give partial credit to that. But full credit means you did everything by the integral test. And another thing to keep in mind is if the problem says use the integral test, maybe the series is summation as we go from 0 to infinity of maybe x, n divided by e to the power of -3n. So if I want to test that for convergence / divergence by the integral test, we usually would check all the hypotheses that this function is going to be continuous, positive, and decreasing on the domain from 0 to infinity, just because I chose 0 for some weird reason, or 1 to infinity if it was that. But you don't necessarily have to check those conditions because the problem already said use the integral test. So if the problem says use the integral test, you're fine to assume the hypotheses of that test are met, and they don't have to be checked. But if you like, you could say, let f of x equal x divided by e to the -3x. This is a bad one. Let's let it be positive 3x. Then that would be a continuous positive decreasing function. It's just not something you necessarily have to state. What you do have to do, and be very careful doing, sorry, this problem is getting longer, is the actual work for the integral test is you must have this somewhere in the problem. It's going to be the limit as t goes to infinity of, lower bound here is 1, so we take 1, up to t, x e to the 3x dx. Oh dear, sorry. And you have to have the limit here and the variable t here. And that would be just part of the overall instructions of using correct limit notation throughout the exam. But any questions about that integral test so far? Okay, we didn't quite find the time to go through the entire integral test, but in some sense it's really a review problem since this is in the section on improper integrals from chapter 7. So just find the antiderivative as normal and then take the limit. If you folks have questions still, then I'm happy to stick around. Oh, and I forgot to mention, I do have extra office hours tomorrow. Tomorrow I'll be in tab 268 from approximately 2:45. I have an errand to run in Rigby, so I may be there earlier. If I am, you're welcome to just walk in. But I should be there by 2:45 to 3:30, and from the usual 5:30 after my class that ends at 5:15 to 6:30. So after 6:30, I'll just proceed from the tab to this room. Any questions about that? Okay, if you do have questions, feel free to stick around. I'm happy to help.